Hey, ChemStars, this is Mrs. Valoy bringing you the rest of Chapter 4, Section 3. So we spent quite a while practicing electron configuration and orbital notation. And we want to just let you know that there's a few exceptions to electron configurations and why do they occur? Well, it's truly all about stabilities, okay? Some actual electron configurations different from those assigned using the Aufbau, the Huns, the polys, all right, because half-filled subshells are not as stable as filled, but they are more stable than others, all right? So the electrons are what's called promoted. Promoted means I'm moving up step, right? So we're going to move up an electron to make a more stable configuration. So once again, what does letter B tell you? Maybe you want to write this down. Filled and half-filled shells are more stable. All right, so electrons will move to where it's more stable. So for example, let's look at carbon, all right? Let's go back and look at that periodic table. And let's find, I'm sorry, copper, I said carbon. Let's look at copper. Let's go back. Here's copper right here. So I just want to look at its noble gas configuration because all those electrons, the first 18 of them are all buried. I can't get to them. They're not going to be promoted, all right? So right here is where it begins. So 4s2, 3d what? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks like if you were to do this, it'd be 4s2, 3d9. Let's try that. Okay, so 4s2, up, down. All right, 3d9, ready? And go up, up, up. These aren't really nice and neat. I apologize. Up, up. That's 5, 6, 7, 8, 9. So take a look at what I've just done. I have 4s2, 3d9. What's wrong with this? I have a filled shell here, and I have an almost filled shell here. Is there any way I can make this more stable? And the answer is yes. I'm going to take this one right here, and I'm going to promote it to right here. Okay, so remember, I took it from here and I promoted it here. Why is it a promotion? Because it's a higher energy, all right? So what have I accomplished? I have a half-filled shell and a totally filled shell, which is more stable than the filled shell and an almost filled shell, all right? So I promoted over here. So what is it really? Okay, so I just went ahead and I redid it. So this is what it should be, 4s2, 3d9. And what is it really? 4s1, 3d10, all right? Let's go ahead and look at chromium. Here's chromium right here. So what is it? Start over here again, 4s2, 3d1, 3d2, 3d3, 3d4. All right, so 4s2, 3d4. Let's go back. All right, so 4s2, 3d1, 2, 3, and 4. All right, so let's kind of pause and see what I've done here. I have a filled shell and a not close to filled shell, all right? Is there a more stable configuration for this? The answer is yes. So this is what I'm going to do. I'm going to take this one and I'm going to flip it upside down or upside right, I guess, and then I'm going to move it right here. So that's what it should be. All right, because look what I've done now. I have a half-filled and a half-filled. What do you know about a half-filled and a half-filled? More stable than a filled and an almost nothing. All right, so let me go ahead and put this guy back again, and I'll show you what it should be. All right, up here we go. Here we go. So we'll do this. So what should it be? You ready? Should be up and then up, 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 and up. All right, so I have half filled and a half filled, which is more stable than what I have over here. Now look at silver. Let's try silver. So here's silver right here. Well, you know what? It's right underneath copper, isn't it? 5s2, 4d count, 49. So let's see what's going to happen. So 5s2, 4d9. All right, 1, 2. I have some tall arrows here. 3, 4, 5, 6, 7, 8, 9. Huh, isn't that what copper kind of looks like? So what do you think is going to happen? Well, what did copper do? It promoted the 4s into the 3D. What do you think I'm going to do with this arrow right here? I'm going to promote it. So there's all by itself, and I'm going to go 1, 2, 3, 4, 5. Ready? 6, 7, 8, 9. And here's the one we promoted right here. That last one going down is the one that I promoted here. So copper and silver act very, very similarly. So the question is whether elements might show this. Let's go back and look. So here's copper, here's silver. What else might act like it? I bet gold will. Well, what else? Well, look over here. Here's chromium. What other two elements do you think will act like it? How about molybdenum and tungsten and 106, all right? Well, I bet this one here, 112, would also do the same thing. So yes, so anything in the same row as chromium and anything in the same row as copper will have the same tendency to promote like that to become more stable, okay? All right, let's keep going. So there's two more things which I want to show you, and well, that's your valence electrons, okay? So it says, let's visit the electron dot diagram one more time. We're going to determine the valence number of electrons, all right? So what does valence mean? It means outermost electrons, okay? These are the electrons in the highest, most energy level. So find carbon. What is carbon's configuration? Here's carbon right here. Ready? Start here. 1s2, 2s2, 2p1, 2p2. So it's 1s2, 2s2, 2p2. Let's check this out. So it was 1s1, 1s2, 2s2, 2p2. So I want the outermost electrons, okay? So what does that mean? I want the outermost. What's the biggest number? 1, 2, or 2? Well, that's a hard question. It's 2. These are your outermost electrons, okay? So what does that mean? Those are my valence electrons. So how many total do I have? I have 2 here, and I have, it's an arrow, all right, and I have 2 here. So it's 2 plus 2. That's 4. I have 4 valence electrons, okay? So those are the ones I'm going to bond with, all right? So we do electron dot diagram and just start making a box around there. There are my 4 valence electrons, okay? That's my Lewis dot diagram. And I'm going to use that to talk about bonding shortly, okay? So let's finish the period. So here is boron. Boron, these are your, not your outermost, okay? Those are not your valence. So I have valence electrons here. How many valence do I have? 2 plus 1 is 3. Very good. 1, 2, 3. All right, here's carbon. Here are my valence electrons right here. So I have 4. 1, 2, 3, 4. All right. Here are my valence electrons because 2 is my biggest number. These are the inside. They don't count. They don't bond. All right. So how many total valence electrons does nitrogen have? Well, what's 2 plus 3? 5. Okay, watch what I do. I go 1, 2, 3, 4, and I pair up that one. 5. Okay, what about oxygen? How many valence electrons does oxygen have? Well, 2 is my biggest number, so those are my valence. So it's 2 plus 4 is 6. Watch. 1, 2, 3, 4, 5, and 6. So those are my Lewis diagram for oxygen. So over here, how many valence electrons does fluorine have? Well, it's 2 plus 5. 7. Okay, 1, 2, 3, 4, 5, 6, 7. All right. And finally over here, okay, how many total valence electrons do they have? Well, it's 2 plus 6 is 8. Well, it's kind of like a shortcut. And there I go. Okay, so I have 8 valence electrons. Okay, so how is this an advantage? Okay, how many hydrogens can bond with each? All right, the question you need to ask yourself is, well, how many single electrons are there? How many unpaired electrons are there? So in the case of boron, let's scroll this down. How many single electrons do I have? I have 3. So how many hydrogens can bond with that? 3. Carbon, how many single electrons do I have here? 4. How many hydrogens can bond with it? 4. Be careful with nitrogen, it's not 5. How many single, unpaired electrons are there? These are paired up here. Let's start, went back and added that 5th one. So I have 1, 2, 3 single electrons. How about oxygen? I only have 2 single electrons. These are paired, that's single, that's single. I only got 2. All right. How about fluorine? I only got 1 right here. It's my only single electron. How many single electrons does neon have? None. How many hydrogens are going to bond with it? None. That's why they call it a noble gas. So finally, all right, what are the formulas for each of these? So in the case of boron, what's the formula for boron? BH3, right? Because what was the question here? How many hydrogens can bond with them? So in the case of boron, I can have 3. So what do you think the formula for carbon and hydrogen is going to be? Ready? CH4. That's right. What's the formula with nitrogen? Hydrogens and how many hydrogens are going to bond with nitrogen? It is 3. Now watch this. You may not know anything about methane or ammonia. I bet you know what the formula is for hydrogens and oxygens, don't you? How many hydrogens are going to bond with 1 oxygen? That's 2. You recognize that as water. All right, so my Lewis dot diagram shows you why it is H2O, because there's 2 single electrons, 2 unpaired electrons that hydrogen can bond with. All right, take a wild stab. What's the formula for hydrogen and fluorine? If you guessed HF, you are right. And what's the formula for hydrogen and neon? You don't. You can't make a compound with hydrogen and neon, so you don't have one. So anyway, that concludes our information in chapter 5. Nope, I'm sorry, chapter 4. So I hope this was helpful. Don't wait to be great, and we'll see you next time. Bye-bye.